Quality Control Improvement, Module 4, Lecture 1, Control Charts for Variables. Language exercise Lecture 1, I explain the statistical basis for control charts for variables. Reading assignment is Chapter 6 in the Montgomery book, pages 235 to 253. I will add here that Montgomery takes a very high-level, detailed view of this, and for a first time too, this is an introductory course. I'm going to kind of lighten up on some things and give you the basic feeling for how to do control charts. So we're not going to cover everything in this particular chapter. There's a wealth of information. I mean, Montgomery sort of wrote the encyclopedia on the subject, but in my opinion, is too detailed for a first-time analysis through it. It's a very good book to use as a reference book, but it's hard to get through in the limited time period that we have to cover it in this particular class. But we'll do a good job, and you'll have a good feeling for how to apply this in your own situation. And honestly, there's you could get a whole major in this specific topic of control charts. But we'll go through it, and I'll show you plenty of examples, and in the case studies, you'll learn how to apply these rules. So first of all, as mentioned in the last lectures, no two objects can be manufactured exactly the same. And this is not only serves for manufacture process, but any process at all. I don't, if you have a recipe for cookies, for example, they're not, each time you make cookies, they're not going to be exactly the same because some of the ingredients may be slightly different, the temperatures may be slightly different, the quality of the flour, et cetera, if analyzed on enough detailed level, you can spot variation. And variation is normal, it's natural. Every process has variation. The variation can be quite large and noticeable, or it can be very small. Even though all atoms may appear to be identical, with enough precision instruments, you can tell the difference. So here again, what we're trying to figure out, we're trying to determine the difference between natural variation and variation due to assignable causes. So there's a lot of things that can cause variation. Of course, equipment. You can have a piece of equipment that needs maintenance, that needs a part that's starting to wear out that can cause variation. You can have differences in source material for what the product you're actually manufacturing. For example, if you're building picnic tables out of cedar, the cedar wood itself can have variations. You can have environmental effects. Machines can perform differently in the summertime and differently in the winter. And obviously a factor as well as people. People get tired. People unfortunately, they go out and drink at night and they come in not 100%, and they don't exactly operate the machines perfectly every time. They're normal. They're human. They're people. So that can cause variation as well. So all these kind of things we have to kind of take into account. So one method that we use to analyze this variation is the control charts. These can be used to measure any characteristic of a product, such as the weight of a cereal box, number of chocolates in a box, the number of defects in a product. These different characteristics that can be measured by control charts can be divided into two broad categories. One is what's known as variables, which we'll take variable control charts, which we'll take a look at in this particular module. And the second type of control charts are known as attribute control charts, and we'll take a look at that in the next module. So a control chart for variables is used to monitor the characteristics that can be measured and have a continuum of values, which means that they have they're not discrete. They have a decimal point, for example. One way I like to think about these things as well is that a variables control chart measures things that have units. So, for example, a length is so many meters, so many inches. A weight is so many pounds or so many kilograms, etc. A control chart for attributes is used to monitor characteristics that have discrete values that can be counted. These typically don't have units attached with them. For example, the number of broken cookies in a box, the number of dents in a car, you know, a light bulb. It either works or it doesn't work. So it's a yes or no, that kind of thing. All these kind of things are what's known as attributes. So in this particular module, we'll be taking a look at what's known as variable control charts. And again, these plot continuous measurement data such as length, mass, pressure in a time-ordered sequence. There are two main types of variable control charts. Data that are collected in subgroups, which we'll discuss primarily, and charts for individual measurements. Now, in this particular module, we're only going to look at data sets collected in subgroups because that's the most useful type, in my opinion, and the one you encounter most. The one we're going to look at is what's known as the X bar R control chart. It has two parts. The first part is what's known as the X bar. Now here, I could put it the bar over the X, but sometimes you'll see this written as X bar. This is a mean control chart because it's X bar is a mean value. It's used to monitor changes in the mean of a process or the average of the process, and there's basically two methods to determine the control limits on the control chart. If we know what the population standard deviation is, then we can use the following sets of three equations to get the upper control limit, the center line, and the lower control limit. Now, X bar is simply the mean of the means. And sigma here is the standard deviation, n is the number of samples. Now, we typically do not know what the population standard deviation is because we're sampling from you know, an infinite kind of set. Every day we're going to sample. We're going to sample, so we don't know what. Exactly, we make 100 chairs, for example. We're making, you know, maybe 10 chairs at a time. We don't really know what the overall population standard deviation is. So typically, when we apply this in manufacturing or in any kind of service industry, we're going to use the left-hand columns where we use what's known as the range method. X bar is still the average of the averages. A2 we get out of a table, and I'll show you how to do that as well. And R bar is the range, and I'll show you how to calculate this in an example. So UCL is the upper control limit, LCL is the lower control limit, and CL is the center line, basically, of the chart. The range chart is calculated similarly, but the range chart monitors the dispersion, or a more familiar term is what's known as the variability of a process. And here I give the formula for the upper control limit, the control limit, and the lower control limit. And D3 and D4 we get out of a table again, and our book has an appendix that has the table in it. In fact, here's the table. These are we can look here, you know, basically to determine those constants. We look and on the left-hand column we figure out how many samples we have. So, for example, if we have a process where again, let's go back to making cookies here, and we have an assembly line making cookies, and let's say at noon we take 10 cookies from the production line. That would be our sample here, N. Then we would come over here to the right. We'd follow to the right, and we would get the factors for the constants. You know, the D2 and D3 and that sort of constants right off of this chart. And again, I'll show you how to do this in an example later. But I did want to point it out that these constants come from a table in the back of the book. So the standard one we're going to apply is what's known as the X bar and the R control charts, and we use them together. So here's some examples where we have some data, and the first sample we plot the mean, and then we plot the sample range. And then each time we make a sample, we plot those on the chart, and we connect those charts with a dot. X bar is the average of the averages. Now this chart was generated in Minitab, and so it'll do all the stuff for you. All you have to do is enter the data, sort of like enter it in an Excel spreadsheet kind of format, and it'll calculate the upper and lower control limits, and it'll do a lot of the heavy lifting for us. So again, how do we apply these now? So we have our data. We went to Minitab. We plotted an X bar and R chart. We want to plot them together. How do we interpret this? Well, first thing we look at is the R chart, the range chart, because if it's out of control, then the process variation is out of control. The next step would be to investigate the cause of this problem, because again, if the R chart's out of control, well, you can stop there. It's your process is out of control, and so you have to go back and try to figure out what the cause is. And we can use, cause and effect diagram, fishbone diagram, all the kind of stuff, basic tools back from the last module. If the R chart is in control, then we can interpret the X bar chart. If it is out of control, then the process average is out of control. Now, if both of them are in control, well, then we're fine. The process is in control. We always look at the R chart first, and then we look at the X bar chart second. Now, I came up with this analogy that might hopefully kind of help to figure out how this stuff works. So let's say we're making a Thanksgiving turkey, and we're preparing it in the oven, and the instructions say to bake it at 350 degrees. Well, what kind of things can go wrong? Well, one thing that can go wrong is that so this is, the average temperature during cooking could be 250 degrees. It's supposed to be 350 degrees, but if it's baked at 250 degrees, well, then that's a problem. And so this is sort of like the average, right? I mean, so an oven, we set it at 350, but it actually is maybe maybe it gets to 351 and it kicks off the oven heaters, and it goes back down to 349 and kicks it back on. But the oven's not going to stay at 350 perfectly for the entire time you're cooking a turkey. It's going to vary. It's going to sometimes it'll be slightly higher than 350. Other times it'll be slightly cooler than 350. But on average, we say, hey, it's going to hover around 350. Well, one area you could have here is that you think you set it at 350 and it's really cooking at 250, right? That's one kind of problem you could have here, and that's sort of a problem with the average, right? So instead of hovering around 350, it's hovering around 250. That's the problem with the average temperature being wrong. On the other hand, you could have wild fluctuations, right? So instead of being, it could go down to 200 and then kick on the heaters and heat back up to 500 and kick off the heaters. So it's a wide swing of cycling temperatures, but on average, maybe it stays around 350. But either way, you wouldn't want either one of these kind of problems. Either way, the turkey's not going to be properly cooked in the oven, right? So here, the first case, the inaccurate average temperature. So if it was cooking at 250 instead of 350, the X bar chart would catch that. So if for example, we had a thermometer inside of our turkey, and every 30 minutes we went and looked at the thermometer and we wrote that number down, right? Exactly what it was cooking at. If we averaged all, so we plotted it on the X bar chart, that would vary up and down. We would see that variation on the X bar chart. That's how we would detect that something's wrong. Now, the wide swings, where it dipped down to 200 and then up to 500, that's going to be caught on our R chart, our range chart, because that again, the range chart, which you take the biggest number, subtract it from the smallest number, that difference is what we're going to plot. So that's going to detect it on that range chart. So by plotting the X bar chart and the R chart together, that's going to fix the problem. We're going to determine if we have a problem doing that. So this is what we do in the real world. We go out and let's say, here's a situation where we're measuring the hardness of automobile tires. There's a gauge called a durameter that you can actually push. You can detect the hardness. And so let's say we have an assembly line making automobile tires, and at 8:30 we pull 4 tires off the assembly line, and we measure what the hardness is. We compute the sum of the numbers, x1 through x4. We divide by 4, we get the average. The range value comes from the fact we look at the biggest number minus the smallest number. So 55 minus 51, that's 4. Now let's go to, the next hour, we pull 4 more tires off the assembly, and we do exactly the same thing. And we repeat this process for every hour on the hour for every how many samples we want to take. And here on the X bar chart, we plot the average X values. And on the range chart, we plot the ranges. So here we plotted 4 for the R value and 52.8 for the X value. And the next hour, we plotted the next set of dot, and we plotted the 7 up to here, right? And we continue plotting these out and examine our X bar and R chart. Now, of course, Minitab is going to plot all this for us. We don't really have to hand plot this stuff anymore. Thank goodness. So let's take a look at an example here. Let's say we have we have a situation where we have 10 subgroups. We're going to take 10 measurements off the assembly line. This particular example doesn't really say what these are, but these could be inches or some kind of measurement we're taking. So we take three tires, let's say. And so get the X bar average. We 7 plus 4 is 11 plus 4 15 divided by 3 is 5. That gets our X bar average. The range value simply is the biggest number minus the smallest number, so that's 3 in this case. And we repeat this process for every, so maybe this was taken at 9:30, this is taken at 10:30. We repeat this process for every possible one of these. Now, the beauty about Minitab and why I love it so much is that Minitab will calculate the X bar and the R values for us. We don't really have to do that per se. So here, we can go in once we have these values calculated. We can calculate the X bar. That's going to be their center line. That's simply the average of the averages. So we take the X bar column and we add these numbers up and we divide by 10. We get 7.7. The R average value, we find the same way. We take the range values, we add them up, divide by the number there are, which is 10, we get 3.7. So if you're going to use the tables to figure out what the upper control limit and the lower control limit are, we need to find what the values are in our chart. So here we go back to the appendix and we look down through our sample size, and in our samples we selected 3 objects off the assembly line. So that's where the subgroup sample is 3. So every hour on the hour we selected three samples off the assembly line. So that's where the 3 comes from. So we come over and we get the A2 factor here, 1.0223. So it's X bar, which is 7.7, X bar plus A2 times the R bar, 11.5. We repeat this process for the lower control limit for the X bar, and we repeat this process for the R charts. Notice this one's 0 because D3 here is it's 0. These are blanked out, which means they're 0. So we go in and we can plot these values. Here's our X bar chart plotted. You see our center line. We see our upper control limit, lower control limit. And so this again is produced by I don't know if this exact data is produced in Minitab, but Minitab will produce these looking exactly the same. So this is here's our subgroups down at the bottom, right? So this is the first sample we took, subgroup 1, and the last subgroup we took was 10 down here for the values. So once we have our charts plotted, the next question we ask is, okay, how do we interpret this? We understand how to plot these values. How do we interpret what these values mean? And we'll take a look at that in the next lecture.